Hi class, we are now on section 4.4b. We just finished 4.4a. 4.4a showed us how electrons occupy the energy levels and the sublevels that they do. Electron configurations are important because they help determine how an atom behaves. We haven't really covered that yet. That's what you're going to start learning here. A chemical change involves the loss, gain, or sharing of electrons. So understanding the electron configuration enables us to explain how and predict an element's chemical properties. So what's going to happen? The highest occupied electron energy level is the valence level, or I may call it valence shell because in other books they call it the valence shell. In this book they call it valence level. They mean the same thing. So as a general rule, atoms hold up to 8 electrons in their valence. That's the highest occupied level. So their highest level, they can fit up to 8 electrons. So for instance, let's go to the next page. Okay, so argon. Let's start with argon. Argon has 18 electrons. It has an electron configuration that we see here. That's written out. And if you add this all up, this should equal 18. Now, argon has 8 electrons in its valence level. Now, remember the definition is the highest occupied electron energy level. So with argon, we have a 3 and a 3. So if we add these up, that equals 6. Equals 8. That is 8 electrons in the valence shell. We can have a max of 8 electrons in our valence level. Potassium has 19 electrons. So this should all add up to 19. Now we look at, again, definition. Highest occupied electron energy level can be up to 8. Up to doesn't mean it will be. And we see 1 here, which is 4. It has 1 electron in its valence level. So this one has 8, and potassium has 1. Okay, so now let's look at the noble gases. Noble gases are located on the furthest right column of the periodic table, and they have completely filled valence level shells, or valence level. So if we look at helium, helium has only 1 orbital, and its only one highest level is the same only level that it has. So it's 1, excuse me, but it has 2 electrons in it, and that's considered filled because of the fact that in orbital can only hold 2. So even though it is a noble gas, but it can hold 2, and that's that we accept that. The rest of them have 8. So this is a row this is a column going down, but this is a row. So this is row 1, row 2, row 3, row 4. Remember I told you the rows match the numbers? That's where this is starting to come in. So remember the valence shell is the highest occupied level. So this one for neon is 2. If we add these together, this is 8. This is 3. We add these together, that's 8. And this is 4. And even though there's a 3D here, we're not paying attention because 3 is not more than 4. So we have a 2 and we have 6, and this is 8. So helium again has 2 electrons, has a completely filled first level. Neon, argon, and krypton all have 8 electrons in their valence level or valence shell. This is completely filled S and P subshells. These elements are stable and they're not reactive. Generally do not combine with other atoms or form compounds because they're so stable on their own. And that has a lot to do with the fact that they have filled octets. So if you have 8 electrons in your valence shell, call that an octet. An octet is an atom stabilized by having its highest occupied valence energy level filled. We will not see that with the other atoms, but we do see this with the noble gases. So we describe the stability using the octet rule, which states, again, I already stated that. If an atom has 8 electrons, an octet in its valence shell, then the S and P sublevels are completely filled, which is, again, what we see here. So let's take a look at other configurations for larger atoms. So let's start with the 3 elements in row 3. So we pulled 3 elements from row 3, and we have sodium, phosphorus, and chlorine. So if we look at these, we can see that sodium has an atomic number. So if you ever want to know the atomic number, add up the electron configuration or look at a periodic table. So sodium is 11, and we can add that up when we see that that's 11. Then we look at phosphorus, we have 15, and chlorine is 17. So if we look at these electron configurations, the first 2 levels sometimes called the inner electrons, because sodium, the highest now I'm getting confused. Highest occupied valence electron level is 3. So if we look at 1 and 2 on all of these, which is in a maroon color, so you can see here is the maroon. It matches this color of this one here. So we see, and these are all the same. If you notice, they all end at 2p6. And that is inner electrons. The outer ones are called the valence. Excuse me. Okay. So we sometimes call these inner electrons because they don't change. They all have that in common. And they actually have nothing to do with the chemical reactions that occur. So if we add electrons, the change only affects the valence level. It doesn't affect the inner electrons. So nothing happens to any of these. If we add, it's going to add here and outward, here and outward, here and outward. So neon, so if we look at neon, neon has its outer, the highest, I'm going to keep forgetting how to say this, highest occupied, and I don't know why, I know what this is. Highest occupied valence electron has 8. So it is stable, and it matches all of these. So we could actually use an abbreviation with square brackets to replace this, and that is what you see here. So they call, your book calls it noble gas notation. In other places they call it just abbreviated electron configuration. So instead of writing all this out, you can write this because this represents this whole configuration, and then whatever is extra, which is the valence shells, and then you write the valence shells or valence level on the outside. And so don't think you're going to get out of knowing how to do the full one. You have to know how to write the full one, and you have to know how to do the notation. You actually have to know how to do both. So you can write the neon in square brackets for any of these. And when using the notation, we always use the noble gases. So you can't just randomly pull an element and put in a square bracket. It's got to be the noble gases, because the noble gases have a filled octet, which have complete octets in their inner level. So we use abbreviations, noble gas notation. We have to use one of the noble gases in order to use the shortcut way, if that's what you want to call it. But you have to know both of them. You can't do one and not learn how to do the other. Okay, so let's do some examples. So here we have titanium. Titanium, by using the abbreviated notation, we can focus on the outer electrons and not look at the inner electrons, because they really have nothing to do with our chemical reactions. It's only the outer ones, which are in the valence level. And yes, I know that this one is not, but that's okay. There's, again, unfortunately, there's like weird exceptions. But if you're using what fills with argon, then whatever's left over, just leave it. Okay? Because these will play a part, even though this is 3 and this is 4. So we can focus on the outside ones. The outer electrons include the valence level and partially filled D and F sublevels. So we will use those because, remember, 4s is lower in energy than D. That's why it's listed like this. If you remember showing that diagram part. The formation of chemical bonds involves changes in the outer electrons. The inner electrons are not involved with bonding with other atoms, elements, ions, etc. So selenium has 34 electrons. So one, we write out the full electron configuration. Yes, you have to write out the full electron configuration. Then what we can do is the first 18 electrons correspond to the electron configuration of argon. So once we see that we have a filled valency, we have 8 right here. And we can now cut this off and use an abbreviated in order to remove the inner electrons that don't have anything to do with chemical bonding. So we can rewrite this with abbreviated shorthand. We use argon with square brackets, and then we simply bring the rest of it down. And the highest energy level is 4, and those are the valence. But we also keep the 3 Ds and the Ds and the F sublevels. Okay, so I know this is a lot, but trust me, we're going to do a lot of this. So now we're going to look at sodium. So what is the electron configuration of a sodium atom? And what is the electron configuration of a sodium ion with a +1 charge? Now, if you are confused about the ions, please go back to go over the ion section and my slides on it, because I think it will help. But from this point, we're going to start doing ions. So even if you're having some problems, the more we do them, I think it will start making more and more sense. So remember, an ion, either a positive or negative, just means there's an imbalance of electrons. If it's positive, it has more protons than electrons. If it's negative, it has more electrons than protons. All right, so so sodium, ions are particles within an overall charge of a positive or negative one. A neutral sodium atom has an atomic number of 11. And its electron configuration we have here, full electron configuration. What's in blue is the inner, which we can replace with the abbreviated, with the shorthand. Now the sodium ion has a charge of +1. It has 1 electron less. So that means we have to remove the last electron, which means we lose that whole energy level in this case, because the only reason why this energy level is here is because it has 1 electron in it. So it's like we take the chair away from the table. The electron is removed from the valence energy level, which is a 3s. This leaves the electron configuration of 1s2, 2s2, 2p6. This is identical to that of neon, which has energy level of 2 completely filled. So we can either do a noble shorthand of just writing this, and I'll be honest, I've never seen it like this, just this, because this is going even up another whole row, and I don't understand that. So the rules that I've always known it is that sodium is on the periodic table as this one. We kick it out. You always take the nearest noble gas that's closest to it above it, and it's neon. I've never seen this. Okay, so oxygen. Now let's take a look at oxygen. What is the electron configuration of an oxide ion, which has an oxygen ion with a charge of 2-. I know it says -2, but I'm used to 2-. So an oxygen ion is called an oxide, for one, and it has a -2 charge, which means it has more electrons than it does protons. So that accounts for the -2 charge. It has 2 electrons. Oxygen's atomic number is 8. So the neutral configuration is, we have it here, you can see, and it has on the highest occupied level has 6, which is right here. Okay, now I lost my part. The electrons that are gained by the atom fill the lowest available energy shell, and that's what you see here. You see this 2, it accounts, you have to add 2, and we do. So it goes from 2p4 to 2p6. This is also identical to neon. So we can write the noble shorthand abbreviated way as neon. Again, I've never seen them go up another noble gas. I don't like this. We would just leave it as neon. That's the way I've been taught in the other books and as a student. Okay, so now let's look at something interesting, which may be confusing at first. So oxygen gained 2 electrons, and we see that it has an octet, an electron configuration of this with the oxide ion. The neutral has this. Sodium has this as a neutral, and it has this as an ion. Do you guys see there's a trend here? They look exactly alike. Even though this one lost an electron, this one gained 2. But if you look at a periodic table, you will see where these are associated. And there are actually ones on this side, which gained 2 and took it to a noble gas configuration. Sodium's down here, kicked out the 1 level and took it to a noble gas configuration. I should have put a periodic table up on here. But neon, they both have the same electron configuration as neon, even though this is a negative ion and this is a positive ion. So there's a fancy word to explain this that's called isoelectronic. Isoelectronic means that even though they are different atoms or ions, they all have the same electron configuration. They all equal, if it's 10, 2, 4, 6, 10, 2, 4, 6, which makes 10, 2, 4, 6, which makes 10. That's what isoelectronic means. So because this is being introduced, you guys need to remember this, because I have a feeling you're going to have some things in homework. You're going to have to start adding them up and seeing which ones match. And if they match with the number, they are isoelectronic. Gaining, losing, and sharing electrons is very central to chemistry and how we understand how reactions and things go. So this is never going to go away. From this point on, we're always going to have to deal with something with electrons being gained, lost, or shared. Okay, so now I put some extra slides in here. I'm not actually going to break these down because this is where the learning and the effort on your guys' part really comes in. Because I've given you now enough information I'm going to show you. The answers are all here, but I'm not going to go through them the way I have in the past. First thing you need to do, look up the atomic numbers. What are the atomic numbers for these? Which I purposely didn't put. I've been adding more information on these slides in the past. Not anymore. So you need to know what neon is. You need to know what sodium is, argon, and then you need to write out the electron configuration and then identify the valence electrons. This is where like I said, I can't really explain anymore, but, oh, dropping my microphone. However, this is going to show you, shows you the electron configuration. And then remember, the valence is the highest electron orbital. So it's the highest. So this one would be 2. These would be valence because it's a filled. Noble gases have 8. This one, sodium, would be 1. Would be 3 with 1 electron in it. Argon is a noble gas, so it will be energy level 3 with 8 electrons. And potassium is 4 with 1 electron. So I'm giving you answers, but you guys need to learn how to do these on your own. So I would strongly suggest you go back and try to do these and then get to the slide and look at it. How many electrons are required to fill the valence level of most atoms? This may not make sense, but remember I talked about octet? Octet. That was in the first couple slides with the definition. We are trying to obtain 8. 8 is the most stable. 8 is what the noble gases have. Not all of these atoms will have that, or else they would be a noble gas. But everything is aspiring to be 8. That's why oxygen, which had 6, took 2 more. And even though it made it a negative ion, it now has 8 electrons around it. Okay, so what is the correct electron arrangement for phosphorus? Oh, I messed this up. It cut me off. Atomic number is not 1. I repeat, atomic number is not 1. It's 15, if I am right. Some of you guys need to look this up on the periodic table. Let's just say I meant to do this to test if you were paying attention. Not really. I meant to put 15. Somehow my 5 on my keyboard didn't work. Now you would count and determine which one is right. Yes, the answer is there. I'm not going to pay attention. I'm not going to focus on it because I want you guys to go back over these slides and test your knowledge of doing this. Okay, so here in red is the inner electrons for sodium, phosphorus, and chlorine. The noble gas notation is we can use neon with square brackets, not parentheses, square brackets, to replace the inner electrons, which only leaves us with the valence electrons, and in some cases, D and F sublevels. Okay, write the electron configuration for iron using the noble gas shorthand. Identify the inner electrons, the outer electrons, and the valence electrons. Okay, so here's the thing. You can't get to the noble gas in most cases without doing the full electron configuration, especially if it's asking for the inner electrons. Well, I guess you could, because you can take the noble gas shorthand. So here it is. It gives you the noble gas, the shorthand way. It's telling you the inner are all representative of what equals up to argon, which is 18, I believe. Outer is what's ever left, and the valence has the highest level, which is 4s2. So hopefully all of this is making sense. Now write the electron configuration for ions. Now remember, if it's a negative, it means it has more electrons than protons. Look at what the atomic number is, and in this case, add 2. For strontium, strontium is a positive charge. It's a cation. So look up what strontium is and then take 2 away. Why? Because this means that you have more protons than electrons, which leaves it with a positive charge. The charge that shows is telling you that is what is overall, in a sense, ruling in for that element. This has more electrons because it's a negative charge. This has more protons because it's a positive charge. So here is electron configuration. You need to know how to do the full one. You need to know how to do the abbreviated one. Can't get out of it. All right, which of these is the correct electron configuration for scandium? So you're gonna have to look up scandium. Your book gives you abbreviations. I forgot what page it's on. It's going to give you somewhere in here the names and the atomic number. And then you can figure out which one of these is correct. And there's the correct answer. Which of these is isoelectronic with neon? So you need to know what the atomic number of neon is, and then you can start figuring out from here which one matches that. And how many inner, outer, and valence electrons are in a germanium atom? So you're going to need to know what the atomic number for germanium is, and then work from there.